Okay. So we're going to talk about logic and computers. So fundamentally, one of the things that makes computers so strong is logic. And you're probably wondering, what is the connection right now? So what is this connection between this sort of abstract sentences and problem solving we've been doing in this course and what computers do? And that's a interesting thing to wonder about. One way to think of this connection is that the formal languages we've learned are the language of computing. So we don't really think uh, I mean, we don't wake up having thoughts in our head that are exactly the same as the formal sentences we've drawn up in this class. Uh, in the same way that computers have operations and that are exactly the same as the functioning of these well-formed formula that we've looked at. So the thing that's carries over to computing isn't really the syntax of the particular language you've looked at. It's more the semantics or the meaning content, the truth functioning of this language. But there is an important disanalogy to talk about right off the bat, and that's that the language of computing doesn't use true or false for the meaning of the things being computed. uh, Instead, computer circuits and just circuits in general use bits. And operations use logic gates. So those are the physical things on the computer board or inside a CPU that perform operations given certain inputs. All right, first a little bit about bits. How many of you guys have encountered the idea of a bit before? No? Okay. So bits are binary. They're a two-value digit. So a bit can either be 0 or 1. And typically when we count, I mean, the number system we use when counting uses a base 10 way of counting. So binary is a base 2 way of counting. What does that mean? That means that each digit in a number, so let's say we've got a number here. We've got a 4-digit number in our normal way of counting, 3,472. That's a 4-digit number because it's got 4 places, right? And each one of those places can have 10 numbers associated with it, right? And if you think about that, that seems like really fundamental, right? That has to be the way it is. But there's other ways to count. In fact, the fact that we use base 10 is sort of arbitrary. Well, maybe not. So can anyone think of why we use base 10? Like, what is your hypothesis? Like, why did base 10 evolve as the way we count?
We have 10 fingers.
Yes, Judson's got it. So if you think about it, the first way you learn how to count is with your fingers. And that's like a pretty good reason to use base 10, right? We've got something in front of us that we can use to count really easily. All right, so if we only had 2 fingers, maybe, well, or, you know, 2 whatevers, maybe we would have used binary and start, that would be what seems like really an obvious way to count to us. So anyways, an important skill to have, I mean, it's sort of important. You guys don't need to have this skill, but to think about binary, it helps to think about translating base 10 numbers to binary. So one way to think about the digits places in base 10 is like this. So the first digit place is 10 to the power of 0 times 2. And then the second digit place is counting the number of tens in the overall number. 10 to the power of 1 times 7. And then the third digit place is 10 to the power of 2 times 4. And then the fourth digit place is 10 to the power of 3 times 3. And if you add all those together, that operation gives you this number. So each place is counting how many of those numbers exist, or is representing, yeah, the count of each level of scale in the base. So the first digit's counting the base, the first level, right? The ones. And then the second digit's counting how many tens are in the number. The third digit's counting how many hundreds are in the number, and so on. So this is how binary works as well, but the numbers look like this. So a 4-digit number is like this, and this number is 13 in base 10. How did I get that? Well, the first place digit is 2 to the power of 0 times 1, which is 1. And the second place digit is 2 to the power of 1 times 0, which is 0. The third place, no, why is it doing that? Well, the third place digit is 2 to the power of 2 times 1, which is how many 4s are in the number. And the fourth place digit is 2 to the power of 3 times 1. So how do I translate that? Well, the first digit is how many ones, so there's 1 1 in this number. The third place digit is the number of 4s, so there's 1 4. And then the fourth place digit is the number of 8s, and there's 1 8. So if you add all those together, it's 13. So this exercise I just did is just to illustrate what base 2 counting is and what binary digits are relative to base 10 counting. So base 2, if you think about it, if we have an unlimited number of digits, we can represent any base 10 number. it just takes a lot more digits to do that, right? If we wanted to represent 3,472, we would, yeah, we would need like 30 digits, maybe 30 binary numbers. Or sorry, a 30-digit binary number. Actually, probably not that much. Yeah, I think like 12. Okay. So that's all to say that with a binary way of counting, and we could represent facts about numbers using languages like TFL. And this is how. Okay, how do I erase my annotations? Discard. No. Oh, yeah, okay. Clear. Okay. So we talked a bit about the semantics of computing, right? So that instead of true and false, we have binary numbers, ones and zeros. So now a little bit about the semantics of computing when it comes to representing operations or functioning. So in computing, in order to turn or perform operations on inputs into a machine, logic gates are used. So logic gates are these things, or that's how we draw them. And logic gates come with a table of operations. So given certain inputs, they'll produce this output C. You'll probably notice that this table of operations is pretty similar to another thing we used in our class, and that's truth tables. So since truth tables are more or less showing you what well-formed formulas truth functioning is given certain outputs, certain inputs, we can translate those same truth functions from our language to logic gates. So this is the second connection. The first connection was this connection between truth values and binary digits. Okay. So if I was going to turn this table of operations into a TFL operator, which one would it be? Where the ones represent truths and the zeros represent false. Yes, Reese.
Sorry, I was trying to get my mic. It would be like the conjunct.
Yes. So if we were to make a truth table or this in TFL, it'd be something like this. AA.
I have a question.
Yes, Abby.
So this, I mean, seeing as our truth tables already are like, they already have the two values, the true and false. So this conversion is it only useful for computers? like computing, like if you wanted to put this into a computer and have it solve that, or does it have like paperwork like outside of computer use, like converting everything to ones and zeros?
Uh, just computer use, I think.
Because it seems to me that the true or false is already like enough to like just look and see everything.
Oh, right. So we're talking about, I guess, two different things when you have a truth table and when you have an input output table. So truth tables are showing you what a sentence means in a formal language, whereas the input output tables are showing you what a piece of machinery does in a circuit. And there's a lot of analogies between the two, but they're sort of fundamentally about two different things.
The truth table is more of like what we see, like how we map out like a formula, but the input output is kind of how like a computer thinks through. Is that what it is?
Yeah. You can think of it that way, I think. So the input output, so they share this similarity in that formula in our language that we were looking at has is truth functional. That is, their meaning depends on the truth value assigned to the atomic wall form formula, in the same way that the outputs of a computer depend on what you input. Okay. So if I was going to make this into a wall-form formula for TFL, it would look like a conjunction, as Reese says. So we've got true, false, false, false. And so one thing you may note is that since we can go this way, we can also do the opposite, right? We can translate from truth tables to input-output circuit tables. And this is in fact what computer engineers might do when they're deciding how to build a circuit. So maybe they have like some particular functioning in mind and they represent that in a formal language and then turn that representation into a circuit by using these logic gates. So this logic gate's called an AND gate. It's called an AND gate because it gives an output of 1 only when both inputs are 1. So it's similar to the truth functioning of the AND conjunction in English language. And guess what? There's gates for every operator. So can you guys tell me which operators these are similar to? What operator is this first one similar to in TFL? Any takers?
Is that a disjunction?
Yes. Oh wait, no. Yeah, it's not. It's not similar to any operator. I just realized that. But it is similar to, what would it be if we made this into like a TFL sentence or a TFL assertion? So if we were translating this, this is what it would look like. Okay, yeah, Reese, what would you say to that?
It'd be a negated conjunct.
Yes. So negated conjunct. This is called a NAND gate. So not and. So, as you guys may be realizing at this point, what we're coming up with is a way to design circuits based off of TFL expressions. So this is going to be an important thing for doing assignments later. What we're eventually going to do with this is give you guys the ability to build simple circuits using logic, which is pretty cool, right? But in order to do that, you have to get to know the operations of these gates, similar to how, in order to understand doing truth tables, you needed to know the operations of TFL's operators. Okay. So what is this gate similar to? If we were going to put it in terms of like a TFL expression. Yes, Reese.
Disjunct.
Mm-hmm. So if we're going to turn the ones into trues and the zeros into falses, this would be similar to the disjunct. So this gate's called an OR gate. All right, and then this last gate is similar to the negation, and it's called a NOT gate. All right. So this NAND gate is actually very similar to a logical operator that we we haven't used in TFL, but one that exists in other languages called the Sheffer stroke. And it's at least somewhat philosophically controversial, what operators are important to include in language. Part of your homework is going to deal with thinking about this particular operator, but the NAND gate doesn't exist one-to-one with some TFL operator. Instead, it's a more complex compound well-formed formula, so negated conjunction. And negated conjunctions are sort of important because it just so happens with NAND gates, they're one of a really fundamental type of gate in making circuits. There's like, if you want to read about it, you can make any circuit using all the other gates just from using NAND gates, which is pretty interesting. Okay, I've used this word a bunch. What does it mean? So circuits are the heart of computing, and they're stringing together logic gates into circuit boards. So physical things that take as input electric signals that are meant to represent the value 0 or 1. So I think that most circuits, it's a voltage, or it's the voltage that sends that signal. So voltage of 0.5 volts is 0, and a voltage of 5 volts is 1, usually, on a circuit board. And then the physical mechanism in the gates make it so that output depends on the two voltages coming in. So all logic gates, except for the NOT gate, accept 2 and only 2 inputs, and then give 1 and only 1 output. So the 1 output is the same for all logic gates in a circuit. However, circuits can have more than 2 inputs and more than 1 output. So you can have circuits with multiple outputs, and that's obviously important in operations like addition, where you are representing more than 1 digit, let's say. So you might be representing a 5-digit addition. So that would need to be 5 outputs, right? So let's try this on our own and make a circuit. So take this TFL well-formed formula and actually, let's do this together. So I won't get you guys to do this on your own. I'm going to show you exactly what I'm talking about when we make a circuit. So when we're making a circuit, we don't have the physical material, unless maybe you do, to make a circuit using wires and a battery and power supply. But what we're going to do is draw diagrams using the logic gates that we just learned to represent the truth functioning as a input-output functioning for the circuit. So this is similar to, all right, well, the first step in doing this is to translate this sentence into an input-output table. And this is how we do that. So we're just doing that translation is just a matter of doing the truth table for this. So there's only one atomic in this sentence. Oh wait, there's 2. Okay. And instead of true or false, I'm going to assign them 1s and 0s, but use the same pattern that we use for doing truth tables. So negation, FB and FC looks like this. 0, 1, on 1. And FC, main connective, looks like this. 0, 0, 1, 0. All right. So we've got the input-output functioning. So that's what we want our circuit to match. So we're going to try and string together these circuits, the logic gates that we just learned, in order to match that functioning. Okay, so the way we do that is we create 2 input wires representing FB and FC on our diagram. And then starting from the smallest, sorry, there's 3 inputs. So FC again. So 1 wire for each atomic well-formed formula. And then starting from the smallest our least complex well-formed formula, which is this FB and FC, we create a logic gate representing that that well-formed formula. So here's an AND gate, and it has the functioning analogous to that conjunction. We create a wire and then a NOT gate to represent the functioning of this negation. And then that negation is attached to the conjunction, so another AND gate. And we plug in this FC and the value from that more complex well-formed formula into the final AND gate, and our output should match the values circled in the table of operations. And we can verify this using the table of operations for the logic gates a couple of slides back. So when both values are 1, going into this AND gate, the output is 1, which turns into a 0. And then FC is a 1, a 0 and a 1 going into the AND gate, outputs a 0. So that checks off the first line. So all the inputs are 1. The next input is where FB is 1 and FC is 0. So going into the AND gate, that's 0. Going into the NOT gate, that's 1. And since FC is 0, a 1 and a 0 going into this AND gate is 0. So that checks off output 2. Now we look at output 3. So FB is 0, FC is 1. That is a 0 going into this AND gate, and a 1 coming out of this NOT gate. FC is 1 in this case, so it's a 1 and a 1. Output is 1 on that third line of inputs. Finally, the last line of inputs is 0. So we're doing the computing in our head for these for this circuit. That's sort of cool, right? That we can do that. And then the input into this AND gate, or output of this AND gate, 0 for that input. The output of this NOT gate is 1. And then FC's input here is 0. So the output is 0. So we've matched the truth functioning of this formula with a binary functioning of this circuit board by stringing together multiple gates and drawing up this diagram with input wires going to the appropriate gates. And this is actually what these circuit boards, if you look at them at a certain level of detail, will look like. Okay, how much time do we have left? So we do really cool things like create calculators. So here's an example of a 2-bit adder, also called a half adder. And these sort of circuits, when you string them together, make up much more complicated machinery, but this is a rather fundamental little piece of machinery. So what it's doing is taking 2 bits and giving as output the addition of those bits. So if you combine 2 bits together, the most you can get is 2, right? And if it is 2, then that digit needs to carry over to the next digit, right? Just in the same way that if you add 2 single-digit numbers together and get like a value greater than 2 digits, greater than 10, you need to carry that number over to the next spot. Okay. So just to review, here are all the logic gates that you guys learned. So I'm going to upload this lesson onto YouTube. But if you want, you can take a screenshot of this. This is going to be pretty fundamental in the same way that getting to know the TFL operators have been for doing problems so far. So what we're going to do from here on out is solve problems using circuit gates, like try and, create a circuit that functions in the same way as a TFL well-formed formula. Or try and create circuits that perform mathematical operations, which we can do now. And I'll show you some of those circuits later on. And it's really interesting, right? So, I mean, this is a 2-bit adder. It doesn't have that great a function of capability to represent or replicate mathematical addition. But, once we string a bunch of these together or make a more complex circuit, we're able to do things like add, 7 plus 8 equals 15. How would we do that? Well, we need some way to represent, or we need enough of an input to handle counting up to that would be 4 digits in binary. So those are the binary numbers for 7 and 8. And we would need an output that gives 5 digits. So what's this one? 0, 1, 1. Right? So how many gates would that take? Right. Believe it or not, it takes quite a bit of gates to do this operation. But we can do it now. All we have to do is scale up this process that we just learned of designing circuits, and we can make as many gates. I mean, we can do any operation that we so choose. Okay. How much left do we have? Okay, one thing you might have noticed is that some circuits, right, so this circuit that we designed, the functioning isn't unique to that circuit. And what I mean by that is, if you guys remember finding or using disjunctive normal form to find a truth or to find a TFL well-formed formula that fits some truth functioning, there were a bunch of different well-formed formula that could have the same truth functioning as a disjunctive normal form. That just happened to give you a guaranteed step-by-step, really certain way of coming out with one. But if we used our imagination a bit, we could come up with a well-formed formula that had the same truth functioning, but was quite a bit shorter. And the same applies for circuits too. So I showed you guys a process where we translate exactly the operators we found in the well-formed formula to logic gates. But we can combine these input-output tables, or find ways around them to make circuits with less logic gates. And this is actually an activity that computer engineers are really concerned with, because the amount of logic gates you have in a circuit board determines how much energy it consumes and also how fast it produces operations, right? If you're doing, 1,000,000 operations a second, doubling the logic gates is going to, decrease the efficiency by a lot. Okay. So last thing I want to do is try and solve this real life problem with you guys for designing a circuit. So let's imagine a factory has asked us to solve a problem for them. So I'll just read this out to you guys. There's an automatic alarm control for 2 pumps that deliver chemical cleaners from storage containers into a cleaning facility at an industrial plant. It's important for the safety of the operators that exactly one, but not both, of the pumps is turned on at all times. We need a circuit to control the alarm. Sensors carry a 1 to the circuit on wire A if the first pump is on and 0 otherwise, and similarly for wire B in the second pump. The output of the circuit should trigger the alarm by sending a 1 in 2 cases, when both pumps are on and when neither pump is on. So let's design a circuit that behaves accordingly. So the first step we do is we design a table of operations. So this is similar to what we were doing with constraint problems, translating from an English description of a problem to something that starts us off on formalizing or framing that problem. So here's the operation that we need. The output of the circuit should trigger the alarm in 2 cases, when both pumps are on and when neither pump is on. So it should be the alarm output, which is C, should be true when should be triggering the alarm when both pumps are on and when neither pumps are on, right? And should not be triggering the alarm otherwise. So the functioning of this company wants the alarm to tell them if the pumps are either both on or neither on. All right, so what's going to help us figure out how to design this circuit is to turn this into a TFL waveform formula. So the one that comes closest to the meaning of this is the biconditional. But we don't have a logic gate for biconditional, or one that translates directly to biconditional. So we'll have to think up of something else. Well, one thing we can use is disjunctive normal form, right? So if we think of representing each line as representing a truth condition using disjunctive normal form, we get so we have logic gates that translate from conjunctions to gates. We've got AND gates and we've got OR gates and NOT gates. So now we can proceed with this translation from a table of operations using roughly our formal language TFL to a circuit. So here we have a circuit representing this well-formed formula we came up with. Actually, this doesn't. Let's see. Oh, no, it does, yeah. Okay, so I mean, when you guys are doing this yourselves, there's 2 different ways you can choose to draw up the circuits. So you can make each input distinct or have them joined like they do here. All right, so this shows you more of this process, what we're going to be doing, or what you can do using logic and circuit gates. So far, on Friday, I'm going to go into more detail of this process of drawing diagrams of circuits from descriptions of problems and input-output tables. But what you guys should know so far is really make sure you have in mind this the meaning of these logic gates, the functional meaning of these logic gates, the input-output tables, and the corresponding operators in TFL, because that's going to help you do these problems through translation. Okay, so we're more or less out of time. Did anybody have any questions?
I mean, so you said we're going to go more into the how to create those next class. That's where a lot of the questions. But just to re-go over destructive normal form, you only care about the true values in the truth table, correct? And if there's any false in what makes it true, it's negated, right?
Mm-hmm. Yeah. So when we're doing destructive normal form, we only care about lines where it's on this table of operations where the output's 1 and not where it's 0. So we're representing these two lines, not the other ones. Okay. All right. I'll see you guys on Friday.